So the first one will be a presentation of Professor Christian Helmich, and I will briefly present you with his biography. Professor Christian Helmich is a professor of strength materials and computational mechanics at Vienna University of Technology in Austria. He received his Master of Science and PhD degrees from this university, where he also obtained his habilitation degree for mechanics of materials and biomechanics in 2004. Since then, he served at this university as associate professor before having been appointed as a full professor in 2011, serving now as the head of the Institute for Mechanics of Materials and Structures. From 2000 to 2002, he worked as a postdoctoral associate at Massachusetts Institute of Technology, Department of Civil and Environmental Engineering, supporting the establishment of the field of multi-scale mechanics of bone. Dr. Helmich is the author of more than 80 publications in journals, of 19 book chapters, and of more than 190 contributions to proceedings of international conferences. He has been reviewing for 65 scientific journals and 10 science foundations. He is the editorial board of 8 scientific journals, serving also as the associate editor of the Journal of Engineering Mechanics, and as a corresponding editor of Computer Methods in Engineering and Sciences. His main research interests are centered around multi-scale mechanics of materials and structures with civil engineering and biomedical applications, which concern geomaterials in tunneling, wood, bone, and the skeletal system, as well as the tissue engineering strategies. Related scientific fields include micromechanics, ferromechanics, mechanobiology, and systems biology. His work is appraised by several internationally recognized prizes, including the award for Young Scientist in Computational Engineering Sciences in 2008, the award of the European Community of Computational Methods in Applied Sciences, and an European Research Council grant awarded in 2002, and the Research Prize awarded by the American Society of Civil Engineers in 2011.
Okay, thank you very much. Next time I will send you a shorter CV. That's your fault. Okay, very good. I am very pleased to be here and to have landed on time at 6:30, and then had a wonderful private driver to rush down through a snowstorm, and so in a very fresh state to be here at this important place. When I got this invitation, I was wondering why I was invited, except for speaking about biological materials, being an engineer, computational mechanician, and so on, because we did not work on angiogenesis explicitly. We did not work on fluid flow either explicitly, but I think the interesting thing I can contribute is the following. It's the question about these parameters Nenad was referring to, these material parameters, how to fit them, is it necessary to fit them, or can we get reliable material parameters, structural parameters for biological tissues, right? So the reason why engineering modeling is so extremely successful is that we know our materials. So we know what one piece of concrete is going to do under some loading, or one piece of steel, and so on. And based on that, we can build in the computer the buildings before we build them up, and it works, right? And there is the old dream that to a certain extent we can do the same with our bodies, and we can compute how it would work and how we could intervene in order to make it work better if it doesn't work properly. The field where we did a lot concerning this is, as you see here from the title, is bone. The reason is relatively straightforward. It's probably the material which is best understood and most frequently tested over the last 400 years or so, when they started to do something like this. So there's a lot of experiments around, and we took the challenge to try to put this huge amount of experiments into very few systems or rules which we could mathematically formulate in order to understand the material up to a level that we can hopefully do reasonable computations, so that the games Professor Filipovic was referring to become more and more serious, so that we that we do the transition from a qualitative simulation to a hard prediction, to a hard prognosis. The keyword I will refer to during the next 40 minutes is universal patterns. So each biologist will tell you very fascinatedly that bones are so, diverse, and they are also different, and they can have so many different things and properties, and it's so extremely complicated that you will never be able to govern them mathematically. That's at least what I heard very often when we started to do this work. But the interesting thing is, if you look at the right point, at the right time, and so on, if you get the correct way to looking at these problems, then you do find something which is still universal. So there are rules, there are patterns, there are rules within the entity of all these mineralized tissues, which hold for each and every tissue. So nature has provided us with some fundamental universal properties. Okay, and during the last now 13, 14 years, we have been working intensively of deciphering these rules, and we have collected a few of them, and we hope, and we are very positive actually, and optimistic, that through these structural and mechanical and compositional rules, we can make all these tissues more computable and more predictable, and then in the end, very naturally, help to find solutions for the clinical practice. There were a lot of people involved. I will refer to some of the papers you will see as references. I will not explicitly refer to them during my talk. I just give two names, two ladies who were especially related to about 50% what I do, much more than the other 20 people I could name here. Yeah? Okay, so let's start. Let's start. Does it work now? No? Yes. So, as I said before, I want as a big challenge, as the overall scope, I want to give this challenge concerning the material properties. They are not constant, they are varying in time and space. Wherever you look, you don't know what is the modulus, the strength, and so on. But if you know nothing about them, it's not so reasonable to make a simulation, right? You might not find out so much by the simulation. Okay, but these tissue properties, if you take a piece of bone or skin or whatever, they do depend on the composition and microstructure in them. So, once the microstructure and the composition change, then also the mechanical tissue properties change. So the hope is, if everything is varying, perhaps there is something which does not vary, how the composition and microstructure would govern the mechanical tissues, right? So if the numbers themselves are not constant, hopefully there is some constancy in the functional relationships. So, and this is our basic quest. Let's find some non-changing rules governing composition and microstructure first, and then the composition and microstructure would govern the mechanical tissue. And that's the critical point we got into in the last 4 or 5 years. Not only to think how does microstructure refer to properties. This is the structure property, where all the people are talking about, and where we did a lot of micromechanics. I will put that to the end. But basically to go one step further, to say, okay, the composition and the microstructure itself, they are not fully arbitrary. So it's not that you have any combination of in bone collagen content, and mineral content, or also in vessels and so on. But there are specific rules which govern how much water is doing something with how much collagen, things like this. And this is what I would like to show now in some examples. But before, as another motivation, I go back to classical biology. So coming from Austria, I put some Austrian here, who went also a few years to America, to become famous enough then in Austria to count something. So therefore I say Austro-American, and I can give this talk everywhere. Who's zoologist, right? One of the most famous sea zoologists in the 20th century, important for evolutionary systems theory and so on. And what he says in the middle, actually, where the evolutionary paradigm was extremely strong in the 70s, right? Even at that time, he said, the living world happens to be crowded by universal patterns of organization. So this is zoologists, not the mathematicians, which most obviously find no direct explanation through environmental conditions or adaptive variation. I don't go into philosophy. What that could mean, right? I let you think about it or not. But I stay as an engineer very pragmatic, and I say, okay, the biologist, having a look this for his 80 years lifetime, saying there are a lot of universal patterns of organization in biological systems, always. And therefore, what we do is relatively natural. We say, okay, let's take a mathematical engineering science approach. So we are used to put it into formula, the simplest formula possible, if possible, to identify something like this, universal rules and patterns. Let's start in structural biology, but we also did a little bit in systems biology, and their mechanical consequences. And now we'll first invest some time just talking about universal rules and patterns in structural biology, and then go based on that to mechanics. Okay, so the material I will talk about is bone, which is very well known to a lot of you, which is, as we all know, hierarchical, so at different levels we have different morphological appearances. We have a macrostructure and microstructure. Here in the microstructure is important, we have these big pores, the aversion canals, or these intertrabecular pores. In these pores we have all the living cells swimming around and the growth factors, and they are building up this type of material, and they are eating it up. And then there are also a few cells sitting in these very small pores here, in these small dots. There's one cell per dot. They are the ones measuring what is going on and telling the other cells what to do. Nobody knows precisely how it works, but that's another question. And the material which all these cells builds up is extracellular. So this is out of a cell. It's out of the entities which are living, so to speak. So this material in principle is dead. The material which is used is a structural material that we can stand upright and so on. This bone matrix is extracellular, and it consists always of three components, which makes life easier at that scale. So of water, of collagen molecules. The collagen molecules are almost everywhere where we have structure in our body, right? In the skin, in the vessels, and so on. Very small differences between this collagen and the collagen you have in the cardiovascular field. And then inside you can have here, inside this collagen fibrils, calcium phosphate type materials, hydroxyapatite, which very similar can also be the case in the cardiovascular system once they start to calcify. Okay, so this is all extremely complicated, obviously. So each piece of bone looks a little bit different here, and there's an extreme versatility of bones, right? So the big challenge is now, okay, can we find for these obviously very complex systems at a specific scale rules which are valid for any piece of bone? So let's start with universal pattern rule 1. It's a universal, I always put in quotation marks because in biology it's always very, you can come into philosophical disputes. So it's universal in that sense that for a lot of different tested bone tissues, which you find in literature, that they all obey to these rules, right? It's an experimental observation in the end. Okay, the first thing is what mineral and collagen dosages, so which amount of this organic part and of this part, and also then of water, if we make a relatively simple chemistry view on here, which amount of these constituents are in a piece of bone? Is there any dosage possible, or is it well tuned? Is a very restricted subset of data which are only realized? Okay, and for this we put a purely mathematical and observational situation. So we made use of Science Direct and Scopus and all the other things which are around since 10 or 15 years, right? So you can go back in centuries, and we definitely got back 80 years, so up to the 1920s. And we collected what was there of experimental data. And there are huge experimental databases in the literature, and a small percentage you can really use, but then still not. And what the people did over centuries is the following. They characterized the extracellular bone matrix by different type of chemical tests. The most standard test is dehydration, so you take a piece of bone and then you take out the water by drying it. You have to be careful. If you dry it, if it's too hot, then you burn something else and so on. So you have to look very precisely at the protocols and then to take the most gentle form of protocol, which is there. And afterwards, if you dry it, so then the water is gone. If you afterwards demineralize it, then the mineral is also gone, and then you weigh all these different parts related to the volumes, make Archimedes principle and so on, and you get an idea of the chemical composition of the bone matrix. The same is true for dehydration deorganification, so you solve the organic part, or for dehydration ashing. You burn it, and you hope that the mineral is still there, and the collagen is burned. Okay, go a little bit into detail. It's a little bit delicate. In principle, it's simple. So we have a piece of bone, which is some millimeters, but we are only interested in the part outside the pores. So we put this piece into according to Archimedes principle, into a fluid. Then just the volume of the bone matrix is replaced by the material, right? Then we measure it if the pores are empty in air, and then we get really this extracellular bone matrix density. Then afterwards it is dried. If you know these different masses, the wet and the dry mass, you know the water mass and so on, and that's the first thing. You get here the apparent mass density of water, something like the concentration, chemical concentration of water. And then coming back to these two other type of tests, the most precise one is if you do demineralize, typically in EDA, you really gently take out, wash out all the mineral, and once you don't see any calcium anymore in the fluid which you wash out, and you say, okay, now I lost my mineral, the residue is then the organic mass, and then this is the concentration of the organic material, 90% of which is always collagen, the rest are some other organic materials. And from this we get then the concentration also of the mineral phase. And the last are these dehydration of the second